I'm Don Michaelson, and I will be speaking about monadifying attribute grammars, the work I did with my co-author Eric Van Wyk. These slides are available at z.umn.edu/monads if you'd like to follow along. In attribute grammars, we describe language semantics by associating semantic attributes with nodes in abstract syntax trees. And attribute grammars are used for building actual compilers, not just as formal specifications. So a well-defined attribute grammar needs to always have a result for our semantic analyses, even if the analysis fails. This can make our attribute equations rather complex, since we need to consider both successful and unsuccessful cases. Let's look at a couple of examples from the simply typed lambda calculus that illustrate this complexity. Here we're looking at determining a type for an abstraction. We have an attribute gamma for the typing context, assigning types to names. We also have an attribute tie for the type of a term. Here we're using a maybe type for potential failure, since not all terms are going to be typable. So we have type maybe of type instead of just type type. Here we have a production for an abstraction in our grammar. The abstraction is referred to as top, and it has an argument x of type t1 and a body called t. The body t has the same typing context as the abstraction itself, with the addition of a binding for the argument x. If the body's type is a just, meaning it has a type, we build the arrow type, which is the type of the abstraction. If it is a nothing, meaning the body is untypable, we need to assign nothing to show the abstraction is untypable as well. This would be a simpler equation if we didn't need to match on the body's type, if we could just assume the body was typable. Here we have another example, typing an application in the same attribute grammar. We give the same typing context to both subterms. For the type, we need to use a match to check both that T1 is typable, meaning it has a just type, and that it has an arrow type. Similarly, we need to check that T2 is typable, and that its type matches the expected argument type of the function to determine typability. If any of these conditions are not met, if either subterm is untypable, if T1 is not a function, or if T2's type does not match, we need to give a failure result. Our equations would be greatly simplified if we could assume subterms were typable, and that the term itself is typable, and ignore the failure cases, as we see here, only writing the bare minimum to get the success cases. We can do this by using monads, such as the maybe we saw earlier, implicitly. As an example here, in this equation for abstraction typing, we use t.tie as if it did not have the maybe in its type. We're ignoring the maybe on there and using it as if it had the type inside the maybe. In general, using monads implicitly lets us treat monadic expressions as if they were not monadic. We do this by monadifying equations, so the resulting equations have the expected types and results in a sense of expected that we'll explain later. Since we're going to use monads, we need to say a little bit about what they actually are. A monad is a type constructor with particular operations, which we'll discuss in a moment. They can be used to represent computational effects like potential failure, as we saw with maybe earlier. They can also be viewed as boxes holding values, a very useful way to look at them for our work here. We will write a generic monadic type as m of t, so the m here might stand for maybe or another monad. For our monad operations, our first operation is return, which takes a value and wraps that value in a monad. For maybe, this is just. Bind, which we write infix with these two arrows and an equal sign, takes a monadic value and unwraps the value inside it, then applies the given function to it to produce another monadic value. For maybe, bind checks if the given value is a just, in which case it takes the value inside the just out and applies a function to it, or nothing, in which case it simply passes the nothing through. Our final operation is fail, which creates a monadic value representing failure. For maybe, this is nothing. Because these operations are valid for any monad, Our monadification procedure will work for any monad. We only need the one procedure regardless of the monad that we're going to use. Let's look at a couple of rewriting examples to show how monadification uses these operations. Here we have our implicit equation for typing in abstraction, where we use the body's type directly. This rewrites to bind the body's type into a function which builds the arrow type we wanted when we wrote the original equation. This is actually equivalent to our original equation where we matched on the body's type to decide whether to build the arrow type or pass the nothing through. Our second example is typing an application. Here we have a much simplified equation compared to what we had a little earlier. We match on T1's type directly to check that it's an arrow type. We don't need to consider whether T1 is typable or not. This rewrites to bind the type of T1 into the match with the case that the type is not a function being filled in by the rewriting process of the monadic failure. So if T1 is typable, but it does not have an arrow type, it'll fall through and give a failure value. And this takes care of our failure case without needing to actually write the failure case. That was one of the things we wanted to do earlier. Similarly, we can directly check that T2 has the expected argument type without needing to check whether it's typable. This rewrites to bind it into the equality check because the type of T2 is a maybe and T1 here is not. For the if-then, where we left off the failure case to start with, we need to bind the condition into the if-then-else that we rewrite to get true or false out of the condition. If the two are not equal, we have once again added a failure result. So we're always getting a result from this equation, even though we didn't need to write the failure cases originally. Another monad we might use is the either monad, which is like maybe, but can carry an error message or an error code. Either has two constructors, right, which carries a success value, and left, which carries an error message of some sort. This can be used implicitly to gather error messages while still using the attribute as if it cannot fail. So we can see this in typing the application again. We have the same start. The first two lines here are the same as our previous implicit version, written as if there is no possible failure. But now we have added appropriate error messages in the cases where the subterms are typable, but the application itself is not. We can then match on whether the type of the application is left or right to gather a list of error messages, taking the message to add to our list if the type is a left. So let's move on to some details of how our scheme works. We have three modes: restricted, implicit, and unrestricted, and each attribute is declared to be in one of these modes, with each equation having the mode of the attribute it defines. These modes are important for one of our correctness properties that we'll discuss later. And of the three, only implicit equations are rewritten and are therefore our focus here. All implicit attributes must have a monadic type. That's the purpose of implicit attributes. In implicit attributes, we can use monads implicitly, meaning we can use them as the type inside the monad. We can also only access implicit and restricted attributes, not unrestricted attributes. We have a typing relation to check that these restrictions are followed and that our implicit monad uses are valid, where gamma is a typing context, E is an expression, and tau is a type. Implicit attributes are used for effectful attributes, such as the typing we saw earlier that might not succeed, or for evaluation results. In our other two modes, monads may only be used explicitly, so we can't use a monad implicitly, ignoring the monad's presence. The restricted mode can only access other restricted attributes, hence restricted, and is generally for attributes without effects, but which are still part of the standard language semantics. The typing context we saw earlier would be an example of a restricted mode attribute. The unrestricted mode, in contrast, can use any attribute and is intended for the extras that make the language usable, but the things that are generally not considered to be part of the core semantics of the language. So the things we want in a compiler interpreter, like the errors attribute that we saw earlier for gathering type errors. Our monadification procedure rewrites expressions in implicit equations based on typing. Here, gamma is a typing context, E is an expression, E prime is the rewritten expression, and tau is a type, which is the extended type of E, and the standard type of E prime using the normal typing rules. So there are two things this rewriting does. First, it fills in incomplete matching and if-thens with monadic failures for the unwritten cases, as we saw with typing the application earlier where we matched against an arrow type, and the rewriting added an extra failure case in case it wasn't an arrow type. Secondly, the rewriting also inserts bind and return to make the expression typable. These binds propagate monadic values through the computation. We have a few properties showing our rewriting is correct. First of all, if an expression is extended typable, then there is some expression to which it rewrites, and for any expression to which it rewrites, the rewritten expression has the same type as the original. This ensures that the only errors one needs to fix are those reported based on this extended typing. The rewriting can't introduce type errors into the rewritten expression, nor can it fail for some unknown reason. Another property we have is evaluation correctness. If an expression rewrites and the original expression evaluated, the rewritten expression will evaluate to the same value, where the same is the same value but now with a monadic constructor around the rewritten result. This also goes in the other direction. So if the rewritten expression evaluates, the original expression evaluates to this same idea of the same value as well. So as an example, we have t dot a plus 3, and this rewrites to bind t dot a into a function which carries out the addition. If t dot a evaluated to 4 originally, and to just 4 after the rewriting, our results are going to be 7 and just 7. And these are the same other than the monadic just constructor being added to the rewritten version. We have a prototype implementation of our monadification in Silver, the attribute grammar system maintained by our research group. We use this prototype to implement typing and evaluation for the simply type lambda calculus, as well as type inference for CamelLite, which is a subset of OCaml. We found that the attributes that need to be implicit tend to spread when you write a language. So for CamelLite type inference, the type attribute is implicit because not every expression is typable. And this type attribute flows into the typing context and into the typing substitution. So these attributes need to be implicit as well. However, the spread doesn't end up being a bad thing. It ends up being a good thing. Since you don't need to do a lot of matching to determine whether you have a type or not, you can just assume you have a type and then unify types to get a type substitution, or add a binding to the context to get a new typing context without needing to consider the failure cases. We have an artifact available for anyone interested in trying this prototype out. So due to time constraints, we couldn't cover everything in this talk. There are a lot more details in the paper. It has the full sets of rules for typing and rewriting. It explains why the modes are important to evaluation correctness, and it gives more complete property statements. Currently, our monadification works to rewrite for any monad, but evaluation correctness doesn't hold if the monad can have multiple values inside it. For example, lists used to model non-determinism don't always obey evaluation correctness. A version of evaluation correctness does hold, however, if the value is used only once, which is the most common use case. Also, our scheme currently calls for all attributes to be declared with their mode. However, if only implicit attributes were marked, it should be possible to determine the modes of other attributes based on the flow of attributes through equations. Thank you for coming. Please stay for question time if you have any questions about anything that wasn't clear, or if you'd like to get more details about anything. Thank you.